All right. It's about that time, so I think we're going to kick this off in just a few seconds here. Give everybody a chance to get settled and comfortable, I guess. Right, I'm not supposed to look at that number. All right, so good afternoon, everyone, or good morning, depending on where you are. It's 6 o'clock in the evening here in Richmond Hill, Canada. My name is Kevin Andrews. I am the market manager for indoor mobile mapping at Trimble here at the Atlantic's office in Richmond Hill. And I'm here to talk to you today about mobile mapping for indoor spaces. Hopefully everybody can hear me okay, and we'll get going. So, agenda for today, I'm going to talk a little bit about the challenges of indoor mapping, why we think it's important, why it's not easy, and we'll talk a little bit about indoor mobile mapping, what specifically we're talking about when we talk about indoor mobile mapping. And we'll introduce you to the Trimble Indoor Mobile Mapping System, which is a product from Trimble that has been out for a better part of a year now in production. And we're going to get into a lot more details there. We're going to go right into data collection, some of the real world applications of data collection, how to collect, what some of the different aspects are. We'll talk about the TIMS post-processing suite, which is a piece of software designed specifically for post-processing the data out of the TIMS. We have an extension called the SketchUp Site Publisher, which is a SketchUp extension, allows you to view the TIMS data. We'll talk about 3D modeling and feature extraction, mostly related to Revit. We're going to go a little bit through what the workflow in Revit looks like. We're also going to talk about RealWorks and some of the new features in RealWorks 10.3 that specifically address indoor mapping requirements. And at the end, we'll come back to SketchUp to look at how the modeling and everything comes together at the end of the day. And if everything goes well, we should have a little bit of time left over at the end for questions if you've got them. But go ahead and throw the questions up if you have them. I will address them if I can. I will address as many as I can at the end of the day. And if I haven't addressed your question, then we'll get to you after the fact by email or some other method. So, jumping right into it. So, what is indoor mapping? Really, indoor mapping is about collecting spatial data indoors. And it's really about, we're really focusing here on large facilities, larger spaces. Things like airports and hospitals, shopping malls, schools, things that are large and complex, and they have a lot of requirements for indoor mapping. It could be everything from as-built surveys. Maybe a construction is just completed. You need to validate that the work has been done. Maybe it's an older building and you need to do a property condition assessment. There's asset inventorying. There's collecting data for architectural or renovations, and there's a commercial need or consumer need just for visualization as well. I mean, people are used to having localization or localization-based apps. They're used to having access to spatial and visual information about spaces that they're going to be interacting with, and collecting all that data is an interesting challenge. Why is it a challenge? Because they're big and complex. A lot of our traditional methods tend to either fall apart or be really inefficient. Data acquisition, data processing, traditional methods might include static scanning. They might include just collecting 2D information with distos and other methods there. And the facilities themselves may never shut down. There may always be people in the space, and these are things that we need a solution to deal with all of these challenges. So I'm going to talk about indoor mobile mapping, and mobile mapping is the collection of all this data from a moving platform. It's usually some combination of sensors, LiDAR, camera, maybe even ground penetrating radar, Wi-Fi detectors, cell phone signal detectors, and some positioning system. So in our case, we're going to talk a little bit about the positioning system later, and that's a key aspect. And this isn't really a new technology. I mean, mobile mapping itself has been around for a couple of decades now, usually applied to aerial mapping, land mapping, even hydrography is done with a mobile mapping sense. And it's really about direct georeferencing. We're talking about taking a sensor and directly georeferencing the data. Maybe there's some steps to clean it up after the fact, but that's really the technology we're talking about here. And that brings us to the Trimble Indoor Mobile Mapping System, which we affectionately call TIMS here. And it's a combination of a lot of these things. So we have a panoramic camera, which is the Ladybug 3, you might recognize in black there. We have a LiDAR scanner. The Faro X130 is our standard. We also support a Trimble TX5. And that scanner is locked into a profiling mode, which is an interesting difference, where we don't let the scanner rotate. We're not doing stop and go scanning. We're really doing line scanning in a profiling way. Inertial navigation system, we use a fairly high-end inertial navigation system, fiber optic gyros. It's a very good IMU. Really helps us be robust to a lot of different types of motion, a lot of different types of buildings and floor layouts. All that is wrapped into a nice carbon fiber frame. Done everything we can to keep the weight down. We're running off lithium-ion batteries. All of the data is being written to a removable solid-state drive. And it's on a set of wheels that are instrumented to capture the motion and are also designed specifically for indoor spaces and to be as maneuverable as possible. And what are the benefits of TIMS? It's really all about productivity here, trying to capture as much indoor space as possible. Some of these very large buildings, you could be looking at millions of square feet. And to collect that with traditional methods is just uneconomical. You're going to spend weeks or in some cases months inside these buildings, and that's really not what our clients are looking for. They're looking for a rapid turnaround. They need the information now before the information is stale or out of date. Accuracy, we're in the 2 centimeter range. We're making steps to improve that number every day. Productivity is in the order of hundreds of thousands of square feet per day. We have an excellent case study on our website where we did one of the terminals at LAX. 1.3 million square feet. We did it in 30 hours, 30 hours of on-site data scanning. And the estimate here was that it was going to take in excess of 3 weeks to do it with traditional tripod scanners. So if you're interested in that kind of application, there's an excellent case study we did with a partner called Geospatial out of Los Angeles. And that's on the website there. All right, so we're going to take a look at data collection. And the way that I've organized this presentation is it's quite a lot of video presentations. So we're going to see a little bit about data collection. We're going to see a video about actually see the thing in action. And hopefully that gives you a sense of what data collection is like and what we're trying to do here. But some points about it, some things to look out for as we go into the video. The user has a touch screen in front of him. It's got a nice graphical user interface. He gets to see a map of where he is. He gets to see a status indicator for all of the incoming data. And the operator is going to use known coordinates for geographic registration. So our cart is, because it's based on an inertial navigation system, it needs to know where in the world it is. And if you have precise information, say from a ground control survey, then you can guarantee that you've got day-to-day repeatability without any work after the fact. There's no registration of the point cloud afterwards. There's no dealing with datums afterwards. If everything was collected right in the first place, there's nothing to do after the fact. And we'll get into the post-processing in a couple of slides here. We are going to talk about a 20-minute heading initialization. So our systems, because they're georeferenced, they need to know where north is, but because we use a very good IMU, it is able to resolve north on its own. It's sensitive enough to sense the Earth's orientation and the Earth's rotation and orient itself accordingly. But that takes about 20 minutes. We're going to do that once a day. We're not going to redo it when we change floors. We're not going to redo it when we, after a certain period of time. Once we do it once, it's good for the rest of the mission. Talk a little bit about tie points. Tie points are relative control points that you're going to establish during the mission, and they're points that you may return to. And this is going to help the navigation solution kind of close loops and remain accurate. And we'll see a little bit about some data collection techniques like wanding. Wanding is kind of moving the scanner about to make sure that you're scanning all the areas that you want to scan. And the big question is always stairs. How do you get it up and down stairs? Well, we've put a lot of work into getting the weight down. It's a fairly easy 2-person lift. It's carbon fiber. It's got a lot of handles on it. We think we've made it as easy as possible. However, you do still hope for elevators when you get to a new building. So like I said, so the video is going to take us through project initializations. We're actually going to see what the operator is going to see on the screen. We'll see a video of some different collection techniques. We'll look at going up and down a flight of stairs, and we'll talk a little bit about ground control points. And here we go. So the user interface includes kind of a wizard that's going to take the operator through it. It's going to ask them for things like a job name. It's going to ask them to confirm the date and time. Control points are going to be were programmed into the machine on a USB stick. You're going to create a little text file and put it in when you start up. So this is going to make sure that you're pointing to the right Tim's ground control point file. You can add information after the fact. You can add new points manually if you need to. There's some information in there about floors as well. As you're doing data collection, we're going to segment things by floor, and that'll help in the post-processing step. So here we are selecting a floor, for example. And because the camera is movable, we're also going to enter in a camera height that was measured by the operator as he set up. And here we see a ground control point. Typically in indoor mapping, ground control points are any kind of usable feature. And we don't go driving a lot of pins into the ground. We use recognizable features, and then we've got ground control points saved onto a text file, and that allows us to initialize them. And here we are in our 10-minute initialization. For the sake of the video, we've cut that down quite a bit, obviously. Nobody wants to sit here for 20 minutes. So we'll count that down. At the end of 10 minutes, it'll prompt the user to rotate the card 180 degrees. This just helps zero out some of the biases in the IMU and help it resolve that north orientation better. And as you can see, the user interface is really walking the user through it, telling them what to do at every stage, telling them what to do with the cart, and not letting him proceed until he's confirmed that he's done it. Now in the background here, we see a little bit of what that user interface looks like. We've got a moving baseline on the right, or moving base map on the right. Little blue dot indicates where he is in the building. And you're going to see a breadcrumb trail as he walks about, he or she. And there we go. We've done our initialization, and we're ready to start moving. And here's what it looks like in action. So this is pretty straightforward. Like I say, it's light. The wheelbase is nice and small. It's extremely maneuverable. I mean, it can turn in place. Excuse me. It can get in and out of nooks and crannies. I mean, it's really sort of intended to be able to go into cubicles, to go into supply closets, because these are spaces that need to be mapped. And if we couldn't do it, then there wouldn't be much point. So there's been a lot of effort to make it maneuverable, light, and easy to push around. A question came up. Should the known coordinates be inside the building? It's best if they are. It's not a hard requirement. You can take this thing outside. Like I said, the wheels were designed for solid floors. Cement is okay. Concrete is okay. So the control point can be outside. But if it's inside, it's obviously a lot easier to operate. Now here we are in stair mode. The operator has hit a few buttons to indicate to the system that he's going to be going upstairs. And we need to do this because there are some unusual dynamics, and we need to make sure the navigation system is prepared to handle that sort of information, to tell it that it's not going to rely on the wheels and that sort of thing. And you can see two people without a whole lot of grunting or effort can get it up and down the stairs. Question about lowest ceiling height. We don't really have a recommended limit on ceiling height. We don't require that there be a ceiling. The cart with the camera and its lowest height is only about 5'8" or so. So really, that's your minimum height. A question about Faro scanners. Oh, sorry, metric. The total height is about 1.6 meters at its minimum setting, about 2.1 at its highest setting. No, more than that, sorry, about 2.3 to the top of the camera. The only Trimble scanner we currently support is the TX5, which of course is a variant of the Faro. Right now, the Faro is the only scanner that kind of meets our size, weight, and power requirements for a mobile mapping system. Something like the TX8, well, a very capable scanner. Right now, it's really just too big and power hungry to put on a mobile application like this. Here we see some wanding, and what she's doing with wanding is she's allowing the scanner to see into the building or into the next room before she goes through the threshold of the door. And this is kind of a technique that's stolen from static scanning. When you want to register point clouds together and you're going through a tight threshold like that, you want to be able to see as much of the room ahead of you as you can before you get into there. Because there is a point cloud correction step that I'll talk about later, that same advantage applies to a system like this. Doesn't take a lot of time, just a quick peek into the room before you go. Can we remove the scanner easily to perform other duties? Unfortunately not. Not easily anyways. It was really intended to hold the scanner mechanically stable to the rest of the cart. It's really tightly integrated mechanically. There is a process to take the scanner off and service it, but unfortunately that process doesn't lend itself well to a rapid service in the field. So we don't support a mode, unfortunately, where you might take the scanner off and do a quick 3D scan and then throw it back on and keep driving. That's really just not possible with the way the system is currently configured. Batteries, that's a good question. So we don't have a picture of it, but there are 8 lithium-ion batteries. They're pretty substantial. You can go indefinitely on the batteries because we can hot swap them. So one load of 8 batteries will last about 10 hours, but you can swap 4 at a time as you go and keep them on a charger and collect data indefinitely. Flat areas or slopes. We have no requirement for a flat floor. It works just fine on ramps, on spirals. It doesn't need to be level. It doesn't need to be even. There is no assumptions or requirements for a flat level floor. Question about, sorry, that top one there. Assuming it's better to close each room door as you scan within the room. That's actually not true. Because, well, I guess it depends on your requirements for the scan. If you want to see what the room looks like with the door shut, then yeah, you might want to close the doors behind you. But from a accuracy and scanning point of view, you want to be able to see the rooms outside the room you're in, just to make sure that everything is locked together and there's no possibility of kind of misregistration from one room to the next. Pipes and factory information. It handles as well as any other static scanner. The advantage of this is that you can maneuver the cart quite quickly and get the backside of a pipe or get the pipe from as many different angles as you can. Density may be an issue. We've configured the scanner to run as fast as we can, collect as many points per second on the fastest mirror rotation as we can. But if a lot of detail and pipe work is what you're looking for, then you're probably going to tell your operator to go slowly and make sure that they don't turn too fast, they don't walk too fast, because these are going to affect your point density. And I will be sharing this presentation. Hello, everybody from down under. We are going to be sharing this presentation. A copy of this will be available on this geospatial webinar site, but we can also make the presentation and all the individual videos available to people that ask for it. So, jumping into post-processing. So this is, once the data has been collected, the data comes off of a hard drive. All of it's on a single hard drive, the LiDAR, the camera data, the INS data, so it's all going to come in one package and one folder. And I'll talk a little bit about the theory behind our post-processing. Oh, sorry, I just got one more question. Maximum speed. Is it possible to set up TIMs in a vehicle or on a boat? Unfortunately, the answer to that is no, not in its current configuration. We are kind of hardwired to use the wheels for a bunch of different things. We use the wheels for constraining the navigation solution. We use the wheels for triggering the camera. And we use the wheels for telling the LiDAR to stop logging when we're stationary, so we don't get a whole lot of extra points. So we don't really support a model right now where you put it in the back of a vehicle and use it as a mobile scanning system. And it is not compatible for sort of third-party integration too much. We have some capability to do some time synchronization to external sensors if you want to. It's really more of a customization. We don't have an open interface to people who want to tinker with it, unfortunately. Or fortunately from a support perspective. So to talk about the TIMS post-processing. So there's a couple of different stages of post-processing, and we'll see what that looks like in another short video after that. The first of these stages is to compute the navigation. So this is going to use the INS data, the wheel information, the ground control point and tie point information, and it's going to combine all of those to create an aided INS solution. And for those that are familiar with other Trimble mobile mapping products, you're probably familiar with the Planix POSPAC software. We are using a form of POSPAC to produce a smooth best estimate of trajectory, or SBET file. But in our case, this is just the first approximation. So that's going to get your accuracy down to, half a meter, a few tenths of a centimeters. Not good enough for what people really need. The next step is what we call a point cloud adjustment step. And this goes through generates the point cloud for the given trajectory, and then goes through it point by point, looking for common attributes. Walls, other features that it recognizes, other objects that it recognizes, and really adjust the trajectory to make sure that you only get one of every surface. So no matter how many times you walk up and down a hallway, you're only going to get one version of that wall. You're only going to get one flat surface of the wall. And this is the step that really gets us down into the centimeter level of accuracy. But all of this is completely automatic. If things were collected properly in real time and doesn't need any intervention, then these two steps are going to be completely automatic, and we'll see that in a second. The final stage is simply output your deliverables. And our deliverables include a sort of 2D georeferenced raster image of the floor plan. This is just a horizontal slice through the point cloud. It's really a rapid check of the georegistration and coverage. You can throw it into just about any mapping or GIS software and ensure that you've got the data where you expect it to be, and that you've covered all of the rooms that you want. We're going to export the point cloud as an LAS file, where we'll even do some spatial sampling for you for different applications and different uses. And finally, we're going to generate some exterior orientation parameters and process the ladybug data to a panoramic JPEG for it. And again, these are all automatic as well. We're simply going to tell the software that this is what we want, and it's going to go off and do it. So we're going to see just that in a video here. We're going to select the project folder exactly as it came off of the cart. One click will run all of the navigation and adjustment routines. And we'll do a quick review of how we did the floor partitioning to make sure that everything that was labeled floor 2 is really on the second floor. Another click to output everything that we asked for it to output, and we're good to go. So it's a pretty short video. We'll just jump right into it. There's really not too much to look at. Now we did shorten this one again. The time frame for processing relative to collecting is about 1.5 to 1. So for about every, it's almost 1 to 1. About an hour of collection is an hour of post-processing. All of the data is georeferenced. Because we've got those control points, which are latitude, longitude, everything else from this point on is georeferenced to those points. So the LAS is georeferenced, and the rasterized image and all of the exterior orientation. You're getting latitude and longitude coordinates for everything. So we quickly went through the INS processing, and we've fast-forwarded again through the point cloud adjustment. That step, for this data set was about 1.5 hours of data collection. The navigation processing and point cloud adjustment was about 40 minutes. If you were quick, you saw a little counter there that said it took about 2,000 seconds or so. And here's a little 3D image of what the different floors look like. So the things that have been colored, or that particular floor partition. We can edit the time if we want. If the operator indicated the floor change at the wrong point, we can simply indicate a new time. We're selecting the output here. We have an option of mono or colored LAS files. We're going to select the LAS here, or the colored LAS. Now for this data set, we collected for about 1.5 hours. We've got about 6 gigabytes of raw data. That's images, that's points, that's INS data. That's going to balloon a little bit through the post-processing, probably about 3 or 4 times the volume once we're all finished. So there, another 15-20 minutes, and we have generated all of the output, and that is post-processing. So as you can see, the operator, if everything went well, the operator of the post-processing software to this point has done virtually nothing. Question about how we get accurate latitude and longitude when you're indoors. If accuracy is a requirement, then it does require a surveyor or somebody to come and do a quick traverse through your building. And this is especially important if it's going to be a job that you're coming back to on a daily basis or a monthly basis. Maybe it's a construction job that you have to return to. Having accurate control in the building is really going to give you that repeatability without a lot of post-processing work. If accuracy isn't a requirement, then a single point is good enough, and it doesn't need to be that accurate. We're looking at 50 to 100 meters, which is a coordinate off your cell phone. That's good enough for basic operation of the system. And can the unit be taken outside the building? So this question just popped up. Yes, it can. So the only caveat to that is that the wheels are designed and intended for a flat surface, a solid surface. So whether it's a finished floor or concrete floor, cement is okay, asphalt is okay. We've even done cobblestone. That came out okay, although it was a little bit of massaging to get everything to work. It doesn't work on dirt. It isn't going to work on gravel. It isn't going to work on grass. That's just not what the system is designed to do. Okay, so moving on. Yeah, a comment about exports, E57 format. We don't support it currently. We've had a lot of requests for it, especially recently. The original design was for LAS, which at the time was the most probably portable system. We are getting a lot of requests lately for E57. It's a good question. But now I'd like to get into a SketchUp extension that we have generated just for TIMS data called Site Publisher. And this is available from the SketchUp extension warehouse. At the moment, we're only supporting 2016, but we're rolling out a 2017 support very, very soon. Sorry, I just lost my train of thought there. So what it is it's an extension for SketchUp that allows you to pull in a TIMS project that has been post-processed, allows you to rapidly view the spherical data, rapidly view the floor plan. And this is typically going to be used to either validate the data that you collected or for a later stage, for somebody who's doing modeling perhaps, it's an excellent situational awareness tool. They're able to go into their spherical images, they're able to look at objects if there's any confusion or doubt about what they are in the point cloud. So we'll get into this a little bit. And we'll just jump into the video here. And really, it's a fairly simple extension to use. We're simply going to save a SketchUp project within the TIMS project folder. And indicate which floor we're going to operate on. We can load multiple floors. We're just going to show you the one for now. And see in a second here as we jump out to, okay. We're going to the project. We're going to import a floor. And like I said before, everything is georeferenced at every stage, so SketchUp automatically recognizes that it is UTM data in this case. The coordinates are all there. Everything is georeferenced. So what it's done is it's pulled in the rasterized floor plan, which, like I said, was just a cross-section of the point cloud, and the spherical images. Each of those little gray bubbles is a spherical image that was collected. So we're going to focus on this boardroom, this triangular-shaped boardroom. That's what we're going to use for the modeling later. Now you notice that there are a lot of images, probably way too many images for it to be useful. So one of the things that we allow for is to decimate those images down to a more usable volume of imagery. So we're simply going to apply a filter and a spatial filter and get rid of most of the images. And this is going to make navigation a little bit easier. We are collecting images every meter. We're collecting images regardless of how many times we go up and down the same hallway. So the images do start to pile up a little bit. And this is the viewer. So this is a Windows-based app tied to SketchUp that allows viewing of the spatial data. Later, you're going to see us actually pull a 3D model into this as well. But at this point, we haven't done any modeling, so all we have access to is the 2D floor plan and the spherical imagery. So really at this point, we haven't done a whole lot of work to do the post-processing, but we're already in an immersive environment so that people can see their space, they can verify that things have been collected correctly and that they've got the space that they want to get. They've got the ability now to go in there and start looking at features, looking at signs on the wall, looking at odd architectural features that they may want to model later, things like blinds and glass partitions. These are things that don't always turn up well in the point cloud themselves, but become relatively apparent once you've got spherical imagery data to validate against. There's a nice boardroom with a big table that we're going to model later. And at any time, we can go back to the 2D mode. We can jump into other rooms, other offices, spy on people as they're working diligently at their desk, that sort of thing. All right, so that's the SketchUp extension, Site Publisher. Like I said, just an easy tool for rapidly viewing and validating the data that you collected. And now we're going to go into a little bit of modeling. Good question there. What happens if there's a person in the building? We don't have any tools that are native to TIMS for blurring out faces if that's the requirement. Having somebody moving around the space isn't going to affect the data collection. If you don't mind, ignoring a bit of blur as somebody walks past the scanner, that's not a problem. Because we're always moving, we're not really worried about the shadows. We can always go back and revisit a space. But if there's privacy issues, then there are a number of tools out there for blurring out faces. So to jump into, sorry, just before we move on, can we use the SketchUp extension for SX10 scanning images? No, right now, unfortunately, the SketchUp extension is exclusively for TIMS data. We haven't expanded it for any other products. All right, to jump into modeling. What we're going to see here is a fairly standard modeling effort done in Revit. That boardroom that we jumped in and out of, we're going to do a bit of a floor plan. We're going to model walls and windows. We saw that interesting glass partition wall. We'll model it, and we'll do a detailed model of the boardroom table, just because we can. This will sort of simulate, maybe when you're modeling other facilities or infrastructure. It's really just meant to be an introductory example for you guys to see this in action. And then at the end of it, or not the end of it, sorry, in the middle of it, the operator is going to jump back and forth to the SketchUp extension just to get a good view of what he's looking at and get clarification as to what he sees. And so we'll kick that off. So as you can see in Revit, it's quite easy to snap walls to the point cloud. Remembering that the points that you see are the inside face of the wall, so we're going to snap some nice straight walls to the spaces that we see are straight. And then later we're going to see an effort to join the walls afterwards. So we're not too worried about where they end at this point. We're just interested in getting some straight edges down. Now, before anybody jumps in here, there's lots of different ways to model from a point cloud. We're providing this example because this is an easy way to do it quickly. Lots of people have their favorite methods. The advantage of using an open format like LAS is that it is supported by most of the software packages out there. So whatever your method is, let us know and we'll work with you to perfect it for TIMS data. So we've quickly laid out a bunch of straight edges. This is fast forwarded a little bit, by the way, in case you hadn't noticed. We're not really this effective, productive. But we've laid out some straight edges. We've rapidly joined them. Some finicky little details in the corners here, but we get a nice image of it in the point cloud, so it's easy to keep moving. Question on the board, will there be any effect if there is a water fountain or bodies of water in the building? No. You may get some reflections off the water from the scanner. Because we're moving, we're collecting data as fast as the scanner will collect it. But that means we can't take advantage of some of the automated filtering techniques that are built into scanners these days. Most of them require a heavy amount of filtering in real time or multiple passes of the same object. So you are going to see some noise due to reflections. As long as you're aware of that, then the operator tends to be pretty proficient simply ignoring it. Can it be used on carpet? Yes, absolutely. To some extent, we've had some issues with really deep shag. Not sure what kind of buildings you're surveying, but most carpet tile, office spaces, not a problem. We have had some issues, like I say, with some really deep shag, because you're really sort of floating on top of a loose surface at that point. This question here, is it able to tie into Tekla? Haven't actually played with it ourselves. Again, with the open data formats, there's nothing you can do in Tekla that you could do with any other point cloud. If Tekla is your application, I'd be happy to talk to you about how we can make that work for you. So here I sort of skipped a bit of it there, but you saw the operator jump back into the SketchUp extension view to get a better idea of what he's looking at, and now he knows that he's modeling a glass partition wall. And he can go in there and start modeling with quite a bit more confidence about what it is he's trying to produce. There we go. Now we're going to jump into the boardroom, just get a sense of what that table really looks like, and we'll start modeling that. Follow-up question on Tekla here. What if Tekla gave you a building reference file, and then you could align the system to it and the designated reference points? Not too familiar with the process you're describing, but it seems like that all the information is there. As long as we can get points to the system in real time, a point on the floor that is tied to your reference system. We still needed an absolute reference coordinates. We still need a latitude and longitude. This is a requirement to the inertial navigation system. But if you can give us a point in latitude, longitude, then everything should just line up. It's an interesting question, and something that I'm more than happy to explore with you offline. We'll follow up after the fact and see what it is you're trying to do there. So we see the operator is modeling the legs of the table. He's going to model the surface of it later. Whether it's a table or a furnace installation or ductwork, and the process is the same. Could be walls, could be cubicle walls. We see a lot of requests for modeling of cubicles as people are reusing their space or taking inventory of the furniture. Oh, good question about how many points are required. Minimum of one. To get a solution out of the system, you only need 1 point to start and stop on. If you have multiple points, though, you're going to get better day-to-day repeatability. So you're really going to be able to come back to the same space, day after day, month after month, and be confident that the solutions will align themselves to each other without any extra work. Good question. So he's modeled the table and then gone to a cross-section view to make sure that he's got the height right. All right. And we skipped some of the modeling, and he's done some extra work there just to make the model more available. Oh, here's a good question. Can you preload control points into the TIM so operators know where to look for them? Say if your survey crew goes through the building, airport facility prior to TIM scanning. Yes, absolutely. In fact, this is the normal operation. So if you're going to create a little text file that has control points and latitude, longitude, estimated accuracy, the operator is going to have to find the first one on the list because the cart doesn't know where it is. But after that, every point is going to be sorted by distance from the operator. So as he approaches a new point, it's going to be very easy for him to figure out which point from the list to select. All right. So that's my BIM creation finished. We haven't done much. It's just a small project. But you can see how this would continue on and scale throughout an entire building if that's what you wanted to do. This modeling effort, I mean, this was just actually, I don't know the time frame. I think it was about an hour, I think, it took him to make this model. All right. I want to talk a little bit about RealWorks. I'm not going to get into RealWorks too much. RealWorks is a whole day's worth of presentation. But there's a really interesting new feature in the latest version of RealWorks, version 10.3, that I do want to talk about. I do want to show a little bit about how to get the data in there and how easy it is to get the data in there. So what we're going to do is we're going to watch it as an operator pulls in the LAS files, which are already registered. We're going to do a bit of trimming to get rid of some of the stuff that we don't want. And then the new feature that we're going to look at is automated indoor classification. Automated indoor classification is an attempt by the system to automatically classify walls, floors, and ceilings separate from everything else. This is a great way to filter out people, filter out furniture, filter out all kinds of noise if all he's really interested in doing is modeling the walls and the space itself. So again, nice little video. We'll jump through that. Now within the processed folder of the TIMS project, all of this is just sort of building in the same project folder. We have an LAS folder that has full density. We've done some spatial sampling to 1 centimeter and 5 centimeter just as a byproduct of the process. In most cases, the 1 centimeter filter is good enough for most of our applications. We can see that from the scanning effort, we've got the parking lot out beside the building. We've even got some of the parking structure for the building of our neighbors across the way. And there is also some darker points, which are an unfortunate result of reflections off of the windows, off of the metal frames around the windows. We do have the capability to do some intensity-based filtering during the data collection process. Being a little bit more aggressive with that might have filtered it out. But in most cases, it's easy to ignore. So we're just going to do a bit of trimming here to get rid of the information that we don't want. So points that were collected, you can see down the stairwell a little bit. So you got some points that are actually on the first floor. We're just going to trim out the second floor area that we're interested in. And there we go. So this is the Atlantics building in Richmond Hill, a nice triangular building, which makes for interesting models and whatnot. So back to the video. We've kind of fast forwarded through the scroll bar. It took about 5 minutes to produce this, maybe a bit less, a couple minutes to produce it. And we can see that we've automatically classified ceilings as green, floors as brown, and the walls as blue. And it's done a pretty good job of filtering out the data. We're going to turn off the walls and turn on the remaining layer. Now the remaining layer is everything else. It's furniture, it's people, it's columns that were too small to justifiably be called walls. It's everything. But for most people that are doing, BIM monitoring or BIM modeling, this is the stuff they don't want. So here's a quick and easy way to filter out your point clouds if all you're really interested in are walls and floors and ceilings. And everything is colorized out of the system. So here's a quick view of those walls and floors with colorization turned on. Now you notice the colorization is a little bit noisy than maybe you're used to from static scanning. This is a bit of an issue with mobile indoor mapping because images were taken from a variety of ranges, a variety of lighting conditions. We are getting a bit of color noise in the solution itself. And this is something that we're working on. It's an interesting area of research for us. It is something to get used to if you're used to static scanning. But it is available for reference and for situational awareness. And that's really all I wanted to show you about RealWorks. Like I said, if we had a day, we could probably do RealWorks, and there's probably some people on the call that could teach RealWorks a heck of a lot better than I can. So we're going to move on from this. The last thing we're going to do is we're going to pull that model back into our SketchUp projects. We're going to use some of the features of SketchUp just to make things look a little more lifelike. And then we'll show you what that model looks like back into our site view application. So like I said, we're going to import the model, we're going to texture the surfaces, and then finally we're going to view the model and everything all together in a final project. Back to the video. So again, because the point clouds were georeferenced, when the modeler pulled them into Revit, his model is georeferenced. So he's going to create a SketchUp project. He's going to use our extension to pull in Tim's data from that second floor again. Everything's georeferenced, nothing to change there. There's that same sort of raster floor plan and imagery. And then his next step is going to be to pull in the model. Now what he's done in Revit is he saved it as DXF, which is a format that SketchUp handles quite easily. So he's going to find and pull in that DXF file. And there, without any effort, he now has his model, his floor plan, and all of his images all neatly falling on top of themselves. You can see he's added some detail in the meantime. We've got a TV in the screen, we've got a plant in the corner. But he's going to go through sort of layer by layer and just start applying some color. If you remember from the panoramic images, our walls really are yellow. Not that yellow, though. Opportunity to make things a little bit nicer, maybe. Glass, I mean, these are all things that SketchUp handles very well. It's a great tool for applying a little bit of texture that really makes the model much more usable as an architectural display, as a real reference tool. It's dropped in some predefined chairs, a television. Here's the Revit version of a plant. Not too exciting. And we're going to replace that with the SketchUp version of a plant, which is much, much nicer to look at. And here it is all together. So as you can see, we're starting to get a fairly good representation of the space that we're in. We can verify that with spherical images. Things are looking pretty good. So again, he's going to go through the process of sampling out some of the spherical images. In this case, we're going to be even more picky. He's rather than just trust the decimation process, we can go in and we can manually select individual images if we want to be very particular about how many images and where they're located. The step here to reprocess the images to a different resolution that more better supports the app, makes things run a little bit smoother. But otherwise, here we are, back into that same viewer. Now we can see that we have a model in the background. So we can jump back and forth between model view, panoramic image view, we can jump up and down from 2D to 3D view. Starting to be a pretty handy tool there. We've got wall edges, if that's what we're interested in seeing. We can turn layers off and on. And we can step out of the model even if we want to use that for navigation. And there we are. That's SketchUp modeling and viewing. So that was my last video. Just to kind of sum up what we've covered here today, I've got a couple of questions on the board that we'll get to. But in summary, indoor mapping has some unique challenges. Big complex spaces make it difficult to be efficient. We try and resolve that with the Trimble Indoor Mobile Mapping System by collecting that spatial data on a moving platform, which allows us to collect large volumes of complicated floor plans very rapidly. We output data in industry standard formats that thus allow us to support a variety of workflows. SketchUp, RealWorks, Orbit GT is one that I haven't talked about here, but is a very interesting product that you're going to hear more about from us in the near future. I can I'll probably do another presentation on Orbit alone. Orbit is another viewing tool and asset extraction tool. That's great for 2D floor plans. It's great for asset inventory and feature extraction. And finally, the Site Publisher is an extension available in SketchUp, which is a great viewing tool for viewing your model, viewing your 2D imagery, viewing your 2D floor plans, and your panoramic images. And that's free for anybody to download, and it's available on the store. So, a couple of other questions on the board. So, what are our main customers? So, and what industries? This is a good question. So, our philosophy here is that what we've got is a scanning tool, not really unlike your static scanner, your other methods, and so any application where static scanning is being used indoors, the TIMs could potentially also be used indoors. So, what kind of spaces do we see interested? Airports, absolutely. Hospitals, large universities, large facilities, anything where the scale of the building makes it unreasonable to do or impractical to do from a statics perspective. We've done manufacturing plants that are being reused or having their space reutilized. We've done water processing. We've done water filtration plants. It's been an interesting mix, but the common theme there is the bigger the better. Airports, we keep coming back to airports. Airports are a great example of a large building that is deceptively complex once you get back into the back rooms, and lends itself well to a mobile platform. The same space is scanned multiple times. It'll only be recorded once. That's not to say that it's only going to be recorded once, but we are processing the data to produce a single wall. Coming back to that same space a week later, now that's an interesting question. So our adjustment process only processes within that mission. So if you need to come back to the space a week later, you're going to get, and that space has changed, I should say. Maybe the walls have been realigned, maybe a piece of equipment has been moved. There's nothing that's going to force the solution to match an older solution, which lends itself well then to progress reporting. It lends itself well to change detection. You're getting a good, clean solution. You're getting repeatability to the ground control points. But if something moves from one day or 1 month to the next, then this is going to be a good method to capture that information and display it after the fact. The last question, can we specify a point spacing when exporting? Yes, it's a couple of extra steps, but we can specify different point spacings during output. Most customers don't. Most customers simply accept the default values and will use other software to do sampling if that's really what they want to do. And with scant minutes to spare, that's the last of the questions I have on the board. So last call for questions, and if there's nothing else, thank you very much for your time. I want to thank the marketing department here for supporting me and supporting this presentation and putting it all on for everybody. Thank the Trimble Geospatial group for making this venue available to us to get new product information out to everybody that's interested. I hope it was worth your time, and thanks again.